Hello everyone, and welcome to a realization. Now, we all know that we're all nerds in here. I mean, come on, just look at us. But I have realized that I may be more of a nerd than I ever imagined. Because while we all are doing physics-based experiments for our projects, I took it one step further. Because I am doing a project on a video game. The game is World of Goo, a puzzle game made by just two guys over the course of 2 years. It is heavily influenced by physics, and it has won a ton of awards, and even Game of the Year from some companies. The objective of the game is quite simple: to build towers using your balls, goo balls, and reach the pipe at the end of the level. Once you reach the pipe, your remaining goo balls will fall in, or else they will suffer a horrible spiky death. It is quite plainly obvious that physics makes a big portion of this game, and I will be explaining each part of it in great detail. First, we'll start off with kinematics. Here we find ourselves in a technological world, and then we're just built up to the pipe there. And these are a special type of goo balls that can be shot. Do you notice anything there? Yes, projectile motion has returned. So right here, let's stop. So you can clearly see the path that the goo took. I'll highlight it right here. It certainly follows the rules of projectile motion because it reaches a high point right there and then will fall and then reach its destination. Using wonderful kinematics, we'll be able to solve exactly what happened here, even with just a few givens. You can see it took about 1.15 seconds to cross that gap, and the gap itself is about 10 meters long. The angle at which the object is launched is about 45 degrees. So using this, we'll be able to figure everything out. Remember these? Yeah, we all love these. So since velocity is distance over time, you can easily find the velocity, both initial and final of x, which is 8.70. Then, since it's a 45-degree angle, that means the initial velocity y is also 8.70. From here, we can use the trusty old displacement formula to figure out delta y, which is 3.52. And then it's just the VF squared formula to find VFy, which is 2.59. From here, you can just use trigonometry to find out the total final velocity, which ends up being 9.08 meters per second, directed 16.57 degrees below horizontal. Next up, we got force, and there is a lot of applications of force in this game, so let's get to it. So let's say you're building a tower here, and you notice it's a little uneven, so stop! Let's find that out now, shall we? Let's just focus on this little area right here right now. And we can use some center of mass stuff to figure this out. So let's just separate into two parts here. M1 and M2 should do. Now it looks like both sides are pretty even, so it's safe to say that M1 equals M2. Now we can use center of mass, or just common sense, to figure out that the support should be right here to keep the tower from toppling over. But let's go back to what it really looks like. It's way over here, so that means that things are not going to be good. The mass on M2's side is going to be pushing downwards, and there's nothing to support it, so the structure is going to fall to the right. I think it's time to watch that in motion now, Sure enough, here it goes, falling over to the right. Let's stop again. Once again, we can break this up into two separate components, M1 and M2. Except this time, M2 is a lot more massive than M1. Because of this, the huge amount of mass on M2, the support needs to be way over here on the right to support all that extra mass. But instead, if you look at the actual tower, it clearly is not, because it's way over here. I think you all know what's going to happen here, but let's watch it anyway. Bwahahaha! Physics-based destruction. Next in our look at force, we return to the technological world and look at this thing here. This thing is really interesting, mainly because of the gravity around it, because it's a lot different than what we're used to. What we're used to is a constant FG, always pointing down towards the Earth. Boom, there's the Earth. But this thing is interesting because it has like a gravitational field around it like this, and anything in this field will be attracted towards it. The arrows represent the FG. So let's take a look at this. When you shoot the goo like this, it wraps around almost like it's in orbit around a planet, and then suddenly splat. What we're used to in physics is a constantly downward pointing FG towards the Earth, but this is completely the opposite, because it's a constantly changing FG, because it's always pointing towards that structure in the center there. It's really quite interesting to see this game offer some new ideas on concepts. Next, we'll be looking at the pipe, the force of the pipe, at the end of the level, and just see how powerful it really is. I mean, this thing is more powerful than the Earth itself. I'll show you what I mean. Yeah, we're back to using normal gravity now. But you can see the pipe is holding the structure up, even though there's really not much support at all for it. Here I slow things down to show you that the structure is falling towards the Earth. This is because right now the FG is bigger than the F pipe, I guess. But once you move the goo and make the structure lighter, that changes things. It looks like it's hovering now. That's because now the FG is the same as the F pipe, because less mass equals less FG. Now when you take another one off, you may notice that the structure goes up towards the pipe. This is once again because mass was taken off and the FG is smaller, and now the F pipe is bigger than the FG. So that means the suction of the pipe is even greater than the force of gravity. Wow. The whole structure didn't get sucked in because it was too wide, but see, once that one is pulled off, the last one will get sucked in. So the last thing we're going to be looking at is momentum. Let's get to it! Alright, we got a tower here, and we want to go to the right, but we're having trouble with that. So exactly how do you do that? Use momentum, of course. Let's focus on the goo ball and the tower here. Let's say that the goo is 1 kilogram. I know that's pretty heavy, but hey, it makes things easy. Let's also say the tower is 15 kilograms. Then smack! Now, since this is a perfectly inelastic equation, or a hit and stick, it looks like this. M1 can be the goo, and M2 can be the tower. The goo was moving at 25 meters per second because it was thrown really fast. And then the tower was moving at negative 1.5 meters per second because it was moving a little bit slower, but the other direction. Do the math and then divide by the masses, and you'll get 0.15625 meters per second. So that means that it will really slowly move to the right. Let's see if that's what happens. And sure enough, there it goes off to the right. Now more goo balls are thrown at it to speed up the process, but the creators of this game really knew their physics well. So I've taken you far and wide through kinematics, force, and momentum to see what physics lay within this game. And there is a lot. Now I have one last question to ask you. Are you a true physics nerd like myself? If so, then this game is just for you. It is extremely innovative, and while the levels start out easy, they will eventually become insane. It will test the true capabilities of your physics mind. World of Goo. For the true physics nerd within you. The game is available for Wii and PC, so pick it up now! Okay. Maybe I wasn't able to urge you to buy the game, but I think I know something that will. Take a look at this. There's a level in the game called You Have to Explode the Head. If that's not the most amazing thing ever, I really don't know what is. So seriously, do yourself a favor and pick this game up now.